Good morning, everybody. I'm Janette Brightwell from Dow Chemical. Appreciate the opportunity we've been given by ARC this week to participate in the conference and specifically to share a little bit about what Dow is doing in the alarm management arena this morning from a user perspective. Before I start with that, a little bit about Dow. There we go. Dow is a large chemical company, global. We combine science and technology with the human element to innovate what's essential to human progress. We've been heavily involved in some divestitures and mergers recently, so these numbers may not be exact this week, even if they were last week. But you can see kind of the size. We have roughly 500 to 700 assets globally, 200 sites, 37 countries, many 50,000 or so employees, about half of them in manufacturing and engineering. And we produce a variety of products, anywhere from batch processes selling into the pharmaceutical and automotive industries that require heavy reporting and compliance requirements, to large continuous processes that run for 7 or 8 years before they take a planned turnaround. And so we have a variety of challenges to tackle there. Our headquarters are in Midland, Michigan, and our largest operating facility is in Freeport, Texas. That's where I'm located. I've been there for almost 30 years now. I work in the Central Engineering Technology Center. I'm the expertise area leader for continuous processes, and I'm also the technical leader for a corporate legacy migration program that we have undertaken in the last few years to migrate our proprietary Dow design control system to commercial systems, and that's about 60% of our installed base still at this point, so it's a large effort. A little bit about how Dow does process control, because this builds into our alarm philosophy, which has been in place for many years. We have developed and utilized a work process methodology called State-Based Control, where we basically program a lot of our operating discipline into our control systems. And this has proven for us to be a competitive advantage, and we've proven this in the amount of time it takes us to start up some of our larger facilities relative to industry benchmarks. And also, we've proven capability to reduce batch cycle times and such by implementing this methodology. And so basically, state-based control or unit-based control is designed to enable the operator, for the most part, to interact with the chemical process at the unit operation level, as opposed to always being at the individual device level. And that's embedded in all of our programs and allows us to operate as if the best operator was on shift at all times. So the way this works is we break the process up into units and define the process state for each unit operation that it will be in at any given time. The process can only move from one state to another when predefined conditions are met. And based on the process state, the control system reconfigures the strategy for each element to match the requirements of the process. So in the design phase of our plants, the first thing we do is we break up the process into individual process units, typically a distillation column, a reactor, something like that. We define the process states for each unit and the paths to move between them and the conditions. And then we define the actions in each process state, such as when to start a pump, when to open a valve, when to activate a PID controller, and when to enable our alarms. And so this concept of dynamic alarming and doing the enable correctly the first time, designing it correctly the first time that Bonnie mentioned is something that's been ingrained in our culture since before 20 years ago when I started in process control. So as far as design principles, these are probably some pretty generic concepts that everybody's familiar with. We do use alarm justification as a structured approach to evaluate each alarm before we program it. We require that when we're installing a new control system and highly recommend it when upgrading a control system. We attempt to implement effective alarms which focus the operator attention on the areas of highest priority, and if we do that right, as Bridget was saying, that can positively impact our safe and efficient operation of the plant. And so when we're designing the alarms, try to keep in mind if we can't identify a specific operator action or action that the control system should take relative to that alarm, you may need to really think about if that's needed at all. If the alarm is needed, we want to make sure that we develop smart alarms with correct set points, deadbands or delay timers to prevent chattering, and enable the alarms only when they are relevant. And in our case, we do that with state-based alarming plus additional conditions in some cases. So when we're designing our alarm strategies, we use within our design documents something called action tables, maybe similar to what other folks do. But we've got the process states across the top here and the different alarms down the side. And basically, we look at what the process is doing in each state and determine if each alarm is relevant in that state. So just as a quick example, a high-pressure alarm is probably relevant all the time, unless maybe this is a vacuum column, in which case you don't want to ring a high alarm until you've established your vacuum. Low-level alarm, on the other hand, probably when you're down for maintenance or have just entered a fill type process state, you probably don't want to be telling people you have a low alarm because you just do by definition. So this alarm design concept is something that Dow has historically done, I'll say, pretty well on our projects. However, as everyone knows, life happens, process conditions change, and maybe the alarms are not updated as appropriate and such. And so even well-designed systems can fall into a state where maybe they're not operating as well as they should or they did. And so we do have an alarm rationalization process that we implement. So that's a structured approach to evaluate each alarm in a running facility. So pretty high-level diagram here, but basically we need to generate an alarm report, review the report, compare the key input variables versus performance standards, and if we are okay, then no further action is needed. That's not always the case. And so if we identify issues, there's an alarm resolution process that we can use. And some of the key input variables that we typically monitor are the alarm frequency, duration, top 10 alarms, nuisance alarms, chattering alarms, and potentially others as well. So again, before alarm rationalization can begin, we have to have good reporting. We need an initial reporting baseline and then ongoing reporting at defined intervals so that we can track our progress. The report content, so we have developed, we use mostly an in-house tool that was based on one that we had for our legacy process control system. We've refreshed that recently, and now we can pull in data to that same tool from our legacy plants, as well as our new commercial DCS installations, and the team is working on adding additional capability to pull in data from additional control systems as well into the same tool. So we typically report on alarm duration and frequency, and there are other statistics available as needed for a given plant. And we also track manual interactions and parameter changes because we have found a correlation between a high level of manual interactions and parameter changes and alarms. It's kind of an overall operating philosophy. It either runs smoothly or it doesn't. So most of the monitoring is done at the plant level, and there is some variability, obviously, with 500 or 700 plants in what each plant does. And then our tools have the capability to do some data roll-up, and that is done in some cases in different businesses, and in other cases, different sites roll up their data. And so I receive a copy of a report from one business on a quarterly basis where they list all their plants, they list all the statistics and whether they got better or worse or about the same and how they are relative to their goals. And so various businesses are very actively monitoring all of their plants in that area. Similarly, certain sites do the same thing. There was in the past in Texas operations where I'm located, they did a monthly monitoring of the alarm status of every plant on the site. And if you were the worst one, the production leader got to go explain to the site leader why their plant was the worst one. And you really didn't want to be that guy, and you really didn't want to be that guy 2 months in a row. So that did get a lot of focus. I haven't heard as much that talked about as much recently, so I think it kind of ebbs and flows a bit what different sites do depending on what the priorities are, but there can certainly be some motivation from either the business or the site level monitoring and the leadership really showing that that's important to them. Okay. So once we have our reports, we do have a documented alarm resolution process that the plant folks can use as a guide. It is important to get the right people involved in this. You need someone from process control who can fix the issues, someone from the plant who understands the reasoning, and then also, as I mentioned, the motivation from leadership can be very helpful also. So basic process, select an alarm for resolution out of the report, a bad actor. Is it justified? Is the operator action known? Is it a safety requirement? If there's not a good reason to have the alarm, you probably just want to get rid of it. If you don't need to get rid of it, then how is your instrument? Is it because of an instrument failure? If it is, that's a lot of the causes of our bad acting alarms is we have a problem in the field, so you really need to go get the instrument fixed and make sure it's operating properly if it's important enough to alarm off of. If that's okay, then are the alarm settings still correct? Has something changed in the process such that your alarm settings are no longer appropriate? If it's chattering, you can increase the deadband or delay time. If the enable is not correct, adjust that. Again, things may have changed over time such that what you had before is not adequate. And if it is an alarm that you need and all of those pieces are correct, then maybe you actually have an operability issue in the plant that you need to go address. So you might need some improvement engineers or that type of folks to diagnose the problem at that point. So that's the process we have in place. And again, it's implemented typically at the plant level with various levels of oversight from different businesses and sites. Okay, one other topic I was asked to mention is the implications of migration for controls for alarming, and may have a little bit different perspective here possibly. So in our case, since we have our custom tool and it's not real difficult to configure, typically when we do a control system migration, we don't have a large project also to implement a new alarm management system. We just, set up the data to be pulled into the system that we have. We do have an opportunity to, of course, evaluate all of our control strategy, and we do that in a design phase in what we call a re-engineering step. And so there are some opportunities to take advantage of some of the features of the new control systems where it's very easy to configure alarms, and there's some things that we change based on how our legacy system is set up, and I'll go through that. So in our case, our Dow-designed legacy system had some limitations around alarms. There was only, in the first version of that, there was only a limited number of alarms that you could have on a given system, and that typically averaged out to being less than 1 alarm per I/O point. And so we had a little bit of help, if you will, built in with our alarm justification process, because we just couldn't have, too many. And so we had to be very selective about what we programmed, maybe combine some, really think about what we were doing there. And also our programming language was similar to Fortran, so if you want to write an alarm, you write the alarm. So there's actually effort involved to define every alarm. In our second generation of our control system, that limitation on the hard number went away. So the motivation was a little less now, but you still did have to write every alarm. In the commercial systems, of course, you typically can do object-oriented programming, and it's very easy to configure up to the 5 different alarms with every I/O point just by the click of a box and specifying a set point. And so there's a temptation when you're re-engineering your system of, oh, well, that's easy, I might want that, I might want that. So we have to really make sure that we employ our discipline of alarm justification when we do the re-engineering design for our migrations to make sure that we still, even though it's easy, only configure the alarms that we have, that we need, that will bring value to the operation of the process. And then one other aspect that we need to consider is to ensure that we update any alarm procedures, alarm response procedures that go along with the control system. We have the capability to tie those into our new systems, but there is some work involved to reconfigure some of that. So that can be some work associated with a migration project as well that needs to be planned for and incorporated. And one final point I want to make around alarms and migrations is just the potential implications of subtle differences in the default behaviors between the old and the new control systems. It's very important to understand all the details. For example, how does a high or a low alarm behave if the instrument fails? In our legacy system, we typically implemented our code with templates, and we had a choice. We could choose to make the alarm ring if the instrument failed or suppress the alarm if the instrument failed. There's probably good reasons to do either one, but the point is there may be a default behavior, there probably is a default behavior in your new system that may or may not match how you have your old system programmed. And it's very important to understand that and then have that discussion with the plant. And ideally, we think, if you can, implement the standard functionality of the commercial control system as it comes. You'll save yourself some work, and that's some of the advantage of having a commercial control system, with predefined objects and such, to just implement the functionality as it comes. But you've got to make sure that that meets the needs of the plant, and even if it does meet the needs, if it's a different behavior than they had before, make sure they understand that, they get well trained on that, so they're not expecting either an alarm or even an automatic action that's now not going to happen because of the difference in behavior. And if the default behavior will not meet the needs of the plant, of course, there's the option to customize the code. You can pretty much make it do whatever it needs to do. But there is a price to pay for that, both in the project execution and also in the long-term maintenance. Typically, when you get to upgrading to the next version, some of your customization might cause you some extra work when you have to upgrade to the next version, as well as the work during the project execution. The most important thing is that the alarms meet the needs of the plant, so if you need to customize, you need to do it. But it's just important to study all of the implications and make sure that you understand what you're putting in, what the cost would be to customize, and sorry, I hit something I didn't know I hit, and it distracted me. But anyway, that was my last slide and my last point. And so with that, I will turn it over to Bonnie.